And the answer is not really. It's the processors that are tricking you. So here's the title, The ISA Lies, But You Can Trust It. And let's get back to something we talked about in an earlier lecture. So we talked about the ISA presenting a simple view of the processor. The ISA tells you the processor is atomic, that is, instructions execute one at a time, and it's sequential, that instructions execute in order. And what we're going to see is that this isn't really the case. Now the ISA also tells you something. It tells you that memory is flat. So when you do a load instruction, you assume that any load instruction is going to be just as fast as any other, and this isn't the case either. So let's take a look at what's really going on in the processor. So here's AMD's 8-core Bulldozer processor. You can see there are 4 modules here. Each module has 2 cores. Let's zoom in on one of these modules. So here's the processor core, and it's got a lot of stuff in it. If we look at what's up here, this is the microcode ROM and the instruction decode. This part right here is basically taking x86 instructions and converting them into MIPS-like instructions. So when I told you that x86 was a memory register machine, that's true, but internally it works just like a register-to-register machine. So a load-store machine internally, because it converts the x86 instructions into load-store instructions. We've got some other stuff in here. Here are integer schedulers. And so what these do is they look at instructions and run them out of order. They figure out which instructions can run first or second so that you can get more performance. So now we're breaking the sequential nature of things, because now we're running instructions out of order. All this stuff over here is for running process instructions, and they can run multiple instructions at the same time. So now we're breaking the atomic part, because now we're running multiple instructions at the same time, not having each instruction execute all at once. And then all of these sections over here, these are caches. And the caches are designed to make memory look fast, even though it isn't. Some locations that are in the cache are going to be very fast, and locations that aren't are going to be very slow. So as you can see from this, the ISA is lying to you. The ISA tells you that everything is atomic, sequential, and that all memory accesses are the same, but in the actual hardware, it's not atomic, it's not sequential, and memory accesses aren't all the same for performance, but the processor makes sure that you can pretend that. There's one other really cool thing to look at here, and this is up in the corner here, this gating footer. This right here is one transistor, and that one transistor's job is to turn off power to the core to save energy. So look how big that one transistor is compared to the whole core. That's a huge transistor for turning off power. So before we finish this up here, I want to talk about CISC versus RISC. So we've seen that simple computations are not always simple. So if I want to add a memory location to a register, I have to go load the memory location and add the register and then store it back. Architectures that provide complex instructions to do this sort of thing in one instruction are called CISC, complex instruction set computing. The benefits of these are it's easier to write assembly level programs and you get much denser code because you can choose exactly the complex instruction you want. The cons are the hardware is extremely hard to build. And often you have rarely used instructions that make it hard to make, and the compilers have a hard time using them. So for example, x86 has instructions for manipulating strings, but it's really hard to use a string instruction for anything other than strings. Architectures, however, that only provide simple primitive instructions are called reduced instruction set computing, or RISC. This is like MIPS. And these ones you need a lot of instructions to do simple stuff, but the hardware and the compiler are much easier to design and optimize, and these have really won out. So everything is RISC inside today just because it makes the hardware simpler. And we saw that on the example of the processor from AMD. So let's summarize what we saw about ISAs. The architecture of a processor is what's visible to the program about the machine. Not everything in the implementation is visible. We saw how that Bulldozer processor had out-of-order execution, but that wasn't visible to the program. And the implementation may not follow the architecture. So the architecture says everything's atomic, but the implementation may break that when it doesn't make the program crash. The invisible stuff, sort of the details, is called the microarchitecture, and it's really interesting. These are very big engineering challenges, and there's lots of money to be thrown at them, so people have come up with very clever ideas here. We saw a big piece of the ISA as the assembly language structure, and we saw that we have these instructions that appear to be sequential and atomic. We talked about formats, computation, addressing modes. We talked about CISC with its complex instruction and RISC with its simple instructions. And I want to end our discussion of ISAs by saying basically all recent machines are RISC, and even the ones that appear to not be RISC, like x86, do RISC stuff on the inside. And the reason for this is just too hard to build machines any other way.